let's do this together. So try this problem on your screen.
Okay. Okay, so definite interval of this between this. One half minus 1/3. So okay, so oh. We have to take definite integral. So we have to take the antiderivative. Yeah, I'm kind of stuck here. I'm not sure where to go. Like, I remember doing this problem type. I'm just kind of mixed up in my head now. What's what?
Okay, let's go back to my screen. So I think this is the first step that you went through. This was a good idea. We changed the one fraction into two separate fractions. I think this is something else that you did. This was also a good idea. It's easier for us to work here with exponents rather than roots. So you change these into exponents. Have we taken the antiderivative yet?
Nope.
So I still have to put in the integral sign here. How do you divide two numbers with the same base? You subtract the exponents. I answered my own question, but it sounds like you got that right. So this would be 1/6. That's good that you were careful with the arithmetic and got 1/6 there. And we also know that this is x to the negative 1/3. Have we taken the antiderivative yet?
No.
So we still have the integral sign. So far we were doing good. No mistakes so far. Now, maybe, especially since you were confused, probably the best thing to do now would be to use the sum rule. As we've talked about in the past, when you're confused, one of the best things you can do is take smaller steps. This is really an unbelievably helpful technique in mathematics. When we're confused, it helps to take smaller steps. So the next, take the smallest little baby step you can think of. I'm going to say that again because it's so important. When you're confused, one of the best things you can do is take the smallest little baby step you can think of. So here's one tiny little baby step. Do you see how it's legal to go from here to here?
Mm-hmm.
Yeah. I guess I should be putting ditto signs over here. Now, one difficulty here is what about the 1 and the 8? What about the 1 and the 8 now? By the way, this is what's called the sum rule, right? This is our sum rule for antiderivatives. The integral of a sum is the sum of the integrals. But it would actually get kind of messy to write this, because then we'd end up with two different subtractions. So maybe this is one thing that might have given you trouble here. This is a notation we haven't gone over. I would suggest, I think this is standard notation, now would be a good time to start writing the 1 and the 8 over here. Now would be a good time to start writing the 1 and the 8 over here. So we're going to find this antiderivative and this antiderivative, and then we're going to evaluate it at 8 and at 1 and subtract them. So this is a new notation we haven't used before, but I think it could be helpful to us. So this would be a good way to write that out. That would be a good thing to put in your notes. I think that's a pretty standard notation. So like I say, this would be a good thing to highlight in your notes. We hadn't talked about notation before. That's how we can use the sum rule when we have a definite integral. Okay. Have we taken the antiderivatives yet?
No.
So that's why we still have the integral signs here. Okay, well, we've made these so simple that we should now be able to take the antiderivatives. These functions are now so simple because we've made such clever use of our baby steps that now we should be able to take the antiderivatives. So how could I simplify this term?
Let's see. 6, 7, x. 6 over 7 times x to the 7/6.
Okay, good. That's right. That was the purpose of all those little baby steps, to give us an antiderivative that's so simple that we can get it right, even if we're getting a little confused. Okay, and then what do I write here?
3/2 x raised to the 2/3. Raised to 2/3.
Okay, I think that's right as well. So have we taken the antiderivatives yet?
Yep.
Yeah, so do I need the integral signs now?
No.
No, now the integral signs finally have disappeared because we've taken the antiderivatives. Have we plugged in the 1 and the 8 yet?
No.
So I still need to write this. I still need to write this. The integral signs are gone, but I still need to write this. I haven't actually done that plugging in yet. Okay. So far, so good?
Mm-hmm.
All right, now here's the step where I think you're getting a little confused by this notation. I never really did a very good job kind of slowly introducing this notation here. So what does this notation mean? What it means is we're going to do a subtraction. How do we get this term? We get this term by plugging 8 into this brackets. And how are we going to get this term?
By plugging in 1.
Into that brackets.
Mm-hmm.
Okay, so what should I write here?
6 over 7 times 8 raised to 7/6 plus 3/2 times 8 raised to 2/3.
Does that go in the same bracket?
Yeah.
Yeah, it still goes in the same bracket. And then what goes here?
6 over 7 times 1 raised to 7/6 plus 3/2 times 1 raised to 2/3.
You could have used parentheses here instead of brackets, but I thought the brackets were clear. Okay, so this is again a step to really highlight and meditate on, because I think we're getting a little confused by this notation here. And this is the standard notation. This is how your instructor and your textbook do it. So I think it's important for us to get comfortable with this approach. As we go forward, we really need this notation for the harder problems. So like I said, this is one of the things I would think was confusing on the last problem. So it would be good to go back and think about exactly the notation we used to go from here to here. Okay, so what could we do now? So now we have you could keep brackets if you want. How can we simplify this term?
6/7 plus 3/2.
Yeah, that's a simplification we should make before pulling over our calculator. That's so easy. 1 to anything is just 1, so that term drops out. However, I strongly recommend writing down the 1 first. So definitely don't do this. Don't go straight from here to here. That leads to mistakes. Don't simplify the 1 until you've actually written it down. I think it's really important to actually write down the number 1 and then simplify it. We shouldn't skip that step. All right. Okay, well now would be a good time to pull over our calculator and give that a shot. Now, for our calculator, are there going to be any extra parentheses we need here for the calculator?
We need parentheses for the exponents and also parentheses for the two terms. Well,
so
yeah.
So what are the extra parentheses that we need that we don't already have written down?
We need 2 sets for the 2 exponents.
Anything else?
That's it.
Yeah, that's it. We don't need parentheses for this. We don't need parentheses for this. Remember, when do you need extra parentheses for your calculator? When there's more than one thing in the numerator, when there's more than one thing in a denominator, or when there's more than one thing in an exponent. Those are the only times that you need to add extra parentheses for your calculator. Well, this is a numerator, but there's only one thing in it, so we don't need parentheses here. And this is a denominator, but there's only one thing in it, so we don't need extra parentheses for that. But we do have more than one thing in this exponent. Okay, so talk me through entering that into your calculator.
Okay. I put in a left bracket, 6 divided by 7 times 8, raise the bracket 7 divided by 6, close bracket, plus 3 divided by 2 times 8, raised to bracket 2 divided by 3, close bracket, minus bracket 6
okay, hold up for a second. So let's see. What do you have after the 2 divided by 3?
Yeah, I made a mistake. Okay. I just have 1 bracket. I should have 2.
Right. How can we tell? Well, that's where it helps to have written it down. Notice here we have 1 bracket and then another one. So this is tricky. We just need to take our time and do exactly what we have written down. All right, so let's go back and try again. What should come immediately after the 2 divided by 3?
A bracket followed by another bracket.
That's right. And then what?
One second. I'm trying to fix
take your time. Take your time.
Minus bracket 6 divided by 7 plus 3 divided by 2 bracket, and that should be good.
Okay, well, hope so. All right, and what did you get?
13.34.
Right, that doesn't really look like it's any type of even fraction, but we could check it. Oh, it's some huge fraction. All right, 84,631 over 6,344 is what I got. Well, that's too complicated. It's better just to round this off. So we'll just round this off to about 13.34. Is that what you got?
Yep, and for some reason, I guess not for some reason, but I actually got the same answer when I messed up. I guess that's just kind of lucky with the problem setup, but yeah.
Oh, even when you left out this parenthesis?
Yep.
Okay. there's something screwy there because that should not work at all. Okay, but in any case, we don't need to worry about it. Certainly to be on the reliable method, we need both of those parentheses. All right, something was weird there because it really shouldn't work without that. Okay, so we got the 13.34. Very good. And then we can try that also on our calculator to graph it. So talk me through how you would do that.
Okay, so I'll type in square root, well, I'm going to type in a bracket, square root of x plus 1. Wait, is that? Yeah, it's the same problem. Close bracket divided by the cube root, so I have to go to my math menu, cube root of x, close bracket, graph. It's a weird looking line. Okay.
So you remembered that the cube root is under the math menu. We talked about that before. That's good. You can see my screen?
Yep.
Did you remember to close the parentheses for the square root?
I did not.
So I think that'll probably give us an incorrect answer there. This is tricky. Your calculator puts in an extra parenthesis when it does square roots. Your calculator puts in a parenthesis when it does square roots, so you need another parenthesis there. So try to convert that so that you have what I have here.
Okay.
All right, and then we'll go to Zoom Standard. Does your graph look like this?
Yep.
All right, it's almost a straight line. Almost a straight line. All right, very good. And I think I'm going to go to Zoom Fit to get a better look at that. That I think gives us a better sense. So that gives us a much different sense of what that looks like. Okay. Do we have trace 1, 2? Zoom Fit isn't working the way I thought. All right. That wasn't such a good idea. X min, X max. All right. Well, let's see. So try checking the integral.
Okay. Second calc 7, lower limit 1, upper limit 8, and that gives us 13.34. So yep, looks good.
All right. Now that wouldn't have worked, I don't think, and if we had not closed the parenthesis here for that square root. So that's an important thing to note there for your notes for that problem as well. Okay. So I think there's a real good chance you'll see a problem like this on the test. So let's review the steps here. This is a good problem. I tried to really lay out what the best notation for this is, which we might not have done this carefully before. This might be the first time we really showed all the steps in the notation. So this is a good step problem. Really highlight this in your notes, and after today's session, take your time and really think about each of these steps. So what did you do on your own? You did this step correctly. You did this step correctly. You did this step correctly. So here's where you got stuck on this step. And what went wrong here, here's what went wrong. At this point, I think it seemed like you tried to plug in the 8 and the 1. It seemed like when you got to this point, you tried to plug in the 8 and the 1. That's what was confusing you, I think. Why is it wrong to plug in the 8 and the 1 here? Well, first, you have to take the antiderivative. Only then can you plug in the 8 and the 1. I think that was one of the things that was going wrong there. So we're not ready to plug in the 8 and the 1. One thing that might have hurt you is we haven't gone over this notation. It helps to separate these into two separate groups and take the antiderivative separately. I'm not saying you always have to write the sum rule out like this. You know, if you wanted to go straight from here to here, that's fine with me. If you want to go straight from this line to this line, that's fine with me. But if you're getting confused, then you should include these little baby steps like this. But the key thing is you never actually took the antiderivatives. That's what went wrong when you did this the first time. What went wrong when you did this is you never actually took the antiderivatives. You just plugged in the 8 and the 1 without actually having taken the antiderivatives. Why did you do that? Because I don't think we've been making that mistake in the past, so why did you do that? Well, here's what I think happened. You had already done so many steps that it just felt like, gee, I better plug in the 8 and the 1. What am I waiting for? If you see what I'm saying. You've done this algebra step, you've done this algebra step, you've done this algebra step. You've done so many steps that it felt like it was time to plug in the 8 and the 1. But even though you had done many steps, they were all just algebra. It was only now that you were ready to take the antiderivative. So we had to be a little more patient and wait one more step before plugging in the 8 and the 1. So notice, first, write down the antiderivative inside the brackets with the limits over here, then plug them in. This is the key step to highlight because this is where we got confused. First, write down the antiderivative in terms of x. Then, plug in the 8 and the 1. That was the main thing that was messing us up. And then we saw how to do that here and here. And we talked about how to do this correctly on our calculator as well. Does that make sense now?
Yeah, I was just, I don't know.
Yep, all right, it's easy to get confused. All right, now you still have your calculator with you, right? Press the mode button. Do you see a screen like this?
Yep.
Now, let's scroll all the way down. Do you have a second screen if you scroll all the way down for mode?
I don't.
Oh, so it just stops right here?
Yep, it stops at full.
And you can't get this?
I don't believe so.
Okay, no, I'm sure that's probably right. Okay, so let me show you something here.
My calculator should always be in radian mode for this class, right?
That's right. Okay, so you can't do this on your calculator because you have an old calculator. Do you see how this is better than your calculator? I don't need any, the new calculators, you can just type things in exactly like they are on your paper, and it's guaranteed to be right. Notice here I don't need any extra parentheses. I don't need the extra parentheses around the exponents. I can tell that it's right because it looks exactly the same on the screen as it does here. If you see what I'm saying, 6 sevens times 8 to the 7 6. It's all typed in here exactly like it is on the paper. I don't know, is that, do you see how I would compare those here?
Yeah.
Okay, good. Well, after all that posting, hopefully I typed this in correctly. Let's see what we get. Oh, okay, thank goodness. So this came out correctly. All right, and then, for example, we could go up to this, and here's the function that we had to enter. So we could enter that like, so the point is it has a fraction template. It has a fraction template, so you can actually put things in the top and the bottom. I'm going to put in a square root. Notice this version of the calculator doesn't do that stupid thing about putting in the extra parenthesis that messed you up. Remember that when you did this the first time, you were going to get the wrong answer because you forgot to close the parenthesis that the square root had put in. Well, this new version, it doesn't put in that stupid parenthesis, so you couldn't have had that mistake. Here again, let's see, we'll do the cube root. Let's see how that looks. Here again, it ends up looking precisely like it is on your paper. So you know for sure whether you've typed it in correctly or not. And then we can go to the graph and see it came out correctly. All right, well, I wanted to show you this so you have the option. You know, I know it's late in the game, but you know, you might want to spring for $150 and buy a new TI-84 is my point.
Yeah.
Because it's really kind of holding you back, all these calculator issues. I'm a little hesitant for this because everything takes a little practice to learn how to do it. It takes a little practice to learn how to use this fraction template, for example. It takes a little practice to learn how to do that. So I can't guarantee this would be the best approach here, but I know it really is kind of messing us up here that we can't plug things in directly into the calculator. So it's up to you whether you want to get that for this semester. But I would certainly advise you going forward with your scientific career to buy a new TI-84, basically. The advantage of that, notice, is you won't really have to learn a new calculator because TI-84 is basically the same as you have a TI-83, right?
Yeah.
Yeah. TI-84 is basically the same as the TI-83, so you won't need to learn new keystrokes or anything. But you'll have these templates so that you can type things in directly. I don't know if you're ever planning to take another math class, but you're planning to take physics, right?
Yeah.
It's going to kill you in physics if you're having those calculator mistakes.
Yeah.
Because on physics, you do always have to simplify, right? You always have to simplify in physics. And it's just a huge pain if you can't tell if you're entering things in correctly. So certainly for your physics class, I would recommend buy a new TI-84. And I don't know, it's your choice. You might be better off even just going out this week and buying one for this class. It would be a little bit of a pain because it takes a little bit of effort to learn how to use the fraction templates. But it might be a good idea. Anyway, I wanted to let you know that you have that option. The new calculators are better than the old calculators, and it doesn't take it's except for the templates, you don't really have to learn anything new about using the calculator. It's just an updated version. All right, so I wanted to show you have that option. Okay, very well. So now I'm going to change this back to the old version so that it matches what your calculator looks like. So you have the classic edition. All right.
I just pressed the apps button. I noticed they have sig fig calculator, unit converters. I didn't know this.
Oh, you tried apps? Okay, yeah, you might have a bunch of. My emulator here doesn't have many apps. But yeah, so you might have some interest. It's always interesting to explore your calculator. But I don't think any of those apps will do the math print like we're doing here. So I think you actually need to buy a new TI-84 Plus calculator. Of course, there's other calculators you can get, but you might as well stick with the TI because you already know kind of how to use it, I guess. And that's what I have here on the emulator. Okay, fair enough. All right, so that's that problem. Okay, what I normally do, this problem gave us trouble, so normally I would give you a bunch of reinforcement problems to reinforce this, but we don't really have time for that, so I'm just going to hope that you will practice this type on your own. You should practice, there's a good chance you'll see this on the test. We certainly didn't know how to do this yet. You should practice this on your own, but we won't spend more tutoring time on that. We'll move forward. So let's see, let me give you this. Okay, let's try this problem.
Let's see, the antiderivative of secant x tangent x is secant x plus c. Okay.
Okay, perfect. We went over that yesterday. That's good that you remember that. I'll go back to my screen. Let's try this problem.
This is tangent x plus c. Derivative of tangent is secant squared x. Okay.
Okay, excellent. That's perfect. We talked about that yesterday as well. That's good that you remember that. I'll go back to my screen. Let's try this problem.
Okay, so 1 over cosine is equal to secant x. So
Good. We need those dx's.
Okay, so this gives us secant squared tangent x. Okay.
Let's see. Okay, that was good. It was good there. At first, you were a little bit off on the wrong foot, but you caught yourself and you fixed it. And you came with the right answer. This is something we worked on yesterday. Yesterday, this gave us some trouble, so it looks like you reviewed that and you're comfortable with that now. That's good. This is some pretty important stuff for the test, so that's good that you got comfortable with that. You ended up with the right answer. Very good. I'll go back to my screen. Do derivatives work well for sums? Is this true?
It's not true.
So you'd say this is false?
That's false.
Okay, actually this is true. The derivative of a sum is the sum of the derivatives. You use that all the time. For example, what's the derivative of x to the fourth plus x cubed?
4x cubed plus 3x squared.
Didn't you just use this rule here?
Yeah, I guess so.
Because what you really just did there was this. You just split this up into two separate derivatives. You took the two derivatives separately, and then you added them together, right? We usually don't write it down like this, but that's what you were really doing. This is what's called the sum rule, right? This is the sum rule for derivatives. So is this true or false?
True.
Yeah, that's actually true. True or false?
True.
Things that are true for addition are usually true for subtraction. True or false? Oops.
False.
Yeah, multiplication does not work naturally for derivatives. How would you take this derivative? What is the product rule?
The product rule would be derivative f prime times g plus f times g prime.
Pretty complicated, right? It's certainly not this simple rule here. True or false?
False.
Remember, how would you do this? You'd use the quotient rule, right? Pretty complicated. F prime g minus fg prime o over g squared. So derivatives don't behave naturally for multiplication and division. True or false?
The antiderivative of f plus g equals the antiderivative of f plus the antiderivative. That's true.
One way to remember that is it worked for derivatives, so why shouldn't it work for antiderivatives? There's a sum rule for both derivatives and antiderivatives. If it works for derivatives, there's a good chance it'll work for antiderivatives. True or false?
True.
This is the difference rule for antiderivatives. If something works for addition, it usually works for subtraction. True or false?
Let's see. False.
Now, we haven't really talked about this. We haven't talked about this, but you're right, it is false. You might guess that it's false because products didn't work this simply for derivatives, so why should they work simply for antiderivatives? products don't work simply for derivatives, so why should they work simply for antiderivatives? So they don't. I wanted to bring this up because this is something that at first you were trying to do on this problem. On this problem, you had written this at first. Would this be a legal step?
It wouldn't.
No, you can't just separate the derivatives. This is legal. This is legal if you keep them inside the same derivative. Now you kind of figured that out. You fixed it. You didn't make a mistake. Well, you made the mistake, but you fixed it. But I just wanted to make sure we're clear about that. That's important. True or false?
False.
Okay, I think this is a very important table here to have in your notes. We probably should have talked about this before, but we're going to be taking lots and lots of antiderivatives, so we really need to be familiar with these rules. I hope it won't mess us up to write down false things. So we want to write in very bold letters here, these are false. These are things that people are tempted to do, but you're not allowed to do them. And these are things that are okay to do. We probably should have gone over those rules before. If this is a constant, how could we simplify this derivative?
Just the constant. Okay.
So what's the answer?
Okay.
Okay, that's actually a mistake. I see what you're doing. Okay, fair enough. You're treating this like a variable. If this is a variable, that would work. If this is a function, that wouldn't work. Then you'd have to use the constant multiple rule. But all right, let's leave well enough alone for that. We've talked about the constant multiple rule before. Let's just deal with this for the time being. So this is how addition, subtraction, multiplication, and division work for derivatives and antiderivatives. So like I said, I think this is a very important table. You want to make sure you put that in your notes and meditate on it a little bit. All right, you didn't make a mistake on the last problem, but I thought this was something that came up that we wanted to clarify. Good. Okay, let's try this problem on your screen.
Minus 2. And this is just so this is that, that's that. 1 over cosine times 1 over cosine. So secant x times secant x is secant squared x. Bracket sine of pi divided by 3, close bracket, plus tangent pi divided by 3, close bracket again, minus bracket sine of 0 plus tangent of 0, close bracket again. I get 2.598. Check this. Type in for the function is, let's see, bracket cosine of x, close bracket, raised to, well, yeah, raised to 3, plus 1, close bracket, divided by bracket cosine of x, raised to 2, close bracket, graph. I'm going to zoom fit. Well, this looks like a disaster. Alright, zoom fit.
If it goes to infinity, zoom fit won't work because there's no way to fit it.
Okay.
I think you might as well just stick with the zoom standard here.
Okay, so I'm going to get a second calc. If I can get there. Second calc. 7. 0 to pi divided by 3. Hopefully, now my answer is 5.6829.
So let's go back to your y equals menu and read out to me exactly what you have written down there.
I missed an exponent sign.
Okay.
Okay, so second calc. Zero to, oh, second calc. 0 to pi by 3. And I get 2.598, so that's good.
That's probably why also your earlier graph might have looked weird.
Yeah.
Okay. 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 So anyway, we ended up with that right. Let's stay on your screen for a moment. Well, obviously we got that right because we got the same answer both times. I think this is a pretty tough problem. This is a tough problem. It's kind of similar to the earlier problem that gave us some trouble, except with trig functions. So you had some calculator issues with this, but you did get the right answer. Excuse me. So that's excellent. You did a good job of applying all the techniques we talked about. You were very careful. Now, what's the symbol that tells you when a definite integral? What's the symbol for the beginning of a definite integral?
This
sign.
The
integral sign. And what's the symbol for the end of the definite integral?
The end of the definite integral is respect to.
Yeah, the dx. Good.
Mm-hmm.
All right, now point to your expression that you have in brackets. Have you taken the antiderivative there?
Yep.
So we don't need the dx anymore.
Okay.
Grader might take off a point for that. The dx is only used before you've taken the antiderivative. Okay, but otherwise this was good. I don't think this is an easy problem, so I think that shows some real good progress on some very difficult problems there. There was a bunch of different things that were involved in that. Okay, so I'll go back to my screen. That's good. Okay, so here we go. So let's try this problem. Try this on your screen.
Okay, so then we're taking the antiderivative of this. Okay. Well, 6 and 6, x and 6, 4, x to the 4, 3. Okay, so add 1, 6x, 4, divided by 4, 3, x and c. Okay, I think that's good.
Okay, let's see. Okay, that is good. Excellent. That's exactly right. That's exactly right. I'll go back to my screen. It's good that you remembered the plus c there. Okay, let's try this.
Okay, this is really secant x, derivative of secant x, antiderivative of secant x.
Go back to my screen. I think you miscopied
yes.
the problem.
Yeah. Okay. I was about to say. Okay, so this is really just secant squared x. What gives you secant squared x tangent of x? Let's see. Okay.
All right, let's see. X sine of x. Okay, I'll go back to my screen. Okay, so I just wanted to point out you kind of skipped a step. You went straight from here to here. And you got that right, but we're still having enough difficulty with these problems that this is a step I probably wouldn't skip. We probably should not skip this step. This is better to write down. We're just getting used to this. You might have skipped this because you might not have been sure what the notation for it was. So I wanted to show you, here's a good notation. Here's a notation you can use if you've taken some of the antiderivatives but not all of them. This is a notation you can use when you've taken some of the antiderivatives but not all of them. There's no integral sign here or here because you've already taken those antiderivatives. But there's still an anti-integral sign here because we haven't taken that antiderivative yet. You didn't make any mistakes. You would get full credit for this. You don't need to show this for credit. But we're having enough trouble with the material. It's better to include that step. But overall, that's good. That was a good process, and that was the right answer. So let's move on to the next. Okay, let's try this problem.
Okay, so this is theta plus gives us secant theta. Let's see. Okay.
Okay, that was fast. Let's see. So that pi term is tricky, but you did it correctly. I think some people might have written, I don't know, 1/2 pi squared. But we don't apply the power rule here because pi is a constant. Also, it's good that you use theta and not x. That was good. So there was a couple ways we could have made mistakes here, but I don't think we made those mistakes. Okay, that looks good. Excellent. I'll go back to my screen. Let's try this problem.
Okay, so I'll do one more. This is let me split it and the antiderivative. This. Okay.
Let's see. So this was a problem where we had to do a fair amount of algebra before we took the antiderivative. You did that correctly. And notice we don't apply the power rule to the 1/t. We don't apply the power rule because the power rule doesn't work for t to the -1. Instead, you remembered you have to do that separately and say that that antiderivative is the natural log. It's good you remember the absolute value signs. That's important. So I think we got that exactly correct. Also, you put in t's and not x's. That's good. Okay, so that's not so easy, but you got that right. Very good. I'll go back to my screen. Okay, let's try this.
plus. Okay, so we took the antiderivative, and then we took the okay, so 2 divided by 3 times 9 raised to parentheses 3 divided by 2. And I take that number and I multiply it by square root of 2. Because everything else is zeroed out. I get 25.4558. Graph this. Square root of 2x, close parentheses, graph. Second calc. 0 to 9. I think I need to change my... Yep, okay, cool. Yeah, it's 25.4558. 6, 7.
Okay, let's see. Okay, good. Good. All right, so let's see here. So, okay, this was a problem. We had a little struggle with this last time. These were giving us trouble before, but it looks like you've carefully reviewed that, so that's good. So that's some good improvement on that. The key thing here is to see square root of 2 is a constant. Square root of 2 is a constant, so we just use the constant multiple rule to take it outside of the integral. Do you remember what was going wrong last time? What was going wrong before is we were writing the square root of 2 as 2 to the 1/2 power, and we were trying to apply the power rule. But that doesn't make sense because we don't need that for a constant. We don't need that for a constant. We can just take the constant out of the integral. And it looks like we did that correctly. You simplified away the 0 term before you went to your calculator. I think that's a good idea as well. Let's see. You put the brackets in the right step. Okay, well, again, that's good. That's very good. Not so easy. I'll go back to my screen. That came out correctly. Let's try this.
So tangent, parenthesis, tangent, pi divided by 4, close bracket, plus pi divided by 4, close bracket. I think this is all 0, but just double check. Bracket minus, bracket tangent of 0 plus 0 close bracket. I get 1.785398. So y equals, okay, bracket 1 plus cosine of x raised to 2, close bracket, divided by bracket cosine of x raised to 2, close bracket, graph, and then once it loads, second calc, 7, 0 for lower limit, and pi divided by 4 for upper limit. Hopefully I get that. Yep, I got 1.785392.
Okay, 1 second. Kind of an interesting looking graph. Okay, I got the same answer too. We ended up with the right answer here. Let's look at what you have on your screen. This is not an easy question. I think you were systematic and careful about this. There was one point when you were writing down x's, but you caught yourself and you changed them to thetas. So that's good. Okay, that's not an easy question, but you took your time and you used a good method and you got the right answer. Oh, I did have something else. There's always something else I want to say. All right, so let's stay on your screen for a second. You might not get full credit for this because there's a way to give the answer more exactly. So when you use tangent, do you usually expect the answer to have a pi in it? When you use tangent function, regular tangent, not inverse tangent, when you use a regular tangent function, does the output usually have a pi?
No.
No. Inverse tangent has the pi.
Right.
But here, you still have a good reason to think there's a pi in the answer. How do we know there's a pi in the answer?
Well, because pi wasn't our input?
Well, no.
I don't know.
Because, well, notice there's also a pi over 4 just by itself.
Okay.
You see what I'm saying? That you're not taking the tangent of that. So the tangent of pi over 4 doesn't have any pi's in it, but pi over 4 has a pi in it, and you didn't take the tangent of that. So I'm not sure how picky your instructor is about this. But anyway, let's rewrite this then as a multiple of pi. Try that on your calculator. How would you do that?
So I divided my answer. Wait. I divide pi by my... I divide my answer by pi, and that gives me 0.568. Extend, and then, so I can make this a fraction.
Oh, maybe I'm confused. I thought that would come out much more nicely. What's going wrong here? 1 second.
Okay.
Okay, yeah, my mistake. All right. All right. Well, hopefully your instructor won't care about this. Hopefully they'll let you get by with just the decimal answer. One thing you could do here is, what's the tangent of pi over 4?
Let's see. Tangent of pi divided by 4 is 1.
So what's the exact answer?
1 plus pi over 4.
Let's write that down for your notes. You might want to ask your instructor how picky they are about this. We don't need to spend time on this if they don't care about this. You might want to ask them about this, whether you need exact answers. You could show them this. This is a problem from the website. You could show them this problem and ask whether you need the exact answer or whether the decimal answer is okay. But anyway, let's go ahead and write down the exact answer on the screen for your notes.
Yeah. Here.
Did you write it down?
Yep.
I guess the screen froze up. Okay. All right. Well, anyway, it's there. So that's another trick for getting exact answers we haven't talked about before. Sometimes I've been telling you to do the whole thing in one fell swoop on your calculator, but that's not always the best advice. If you're trying to get an exact answer, sometimes it helps just to do pieces on your calculator. But the best thing is just to ask your instructor whether they care about this. If they'll accept a decimal answer, that's the easiest way to go. But if they want the exact answer, we went over how to do that. Okay, but anyway, that was a good process. I'll go back to my screen. Okay, let's try this.
Okay, so 1, 2, x. I'll just do this on my calculator. Okay, so bracket negative e raised to 0, close bracket, minus bracket, another bracket, negative 1, bracket, raise the 2, minus e raised to bracket, negative 1, close bracket, plus bracket, negative 1, close bracket, bracket again. This is what I get. Okay, let me check this. So y equals 2x minus e to x plus 1, graph. Second calc. 7, negative 1 lower limit, 0 for the upper limit. I get negative 0.632126. They just, I guess, round up. Yep. Okay, cool. I think this is good.
All right, let's see. I fell behind there. 1 second. Okay. Okay. Good. Now, again, we're not sure whether we need exact answers or not. What's negative e to the 0 on your calculator?
That would be negative 1.
So let's just write that down on your screen. Negative 1. And then in the next bracket, you have negative 1 squared. So what's that negative 1 squared?
1.
Good, so we can write that down. And then minus e to the negative 1. Don't bother doing that on the calculator because it'll come out to be a decimal. So just write it as negative e to the negative 1. And then there's another minus 1, right?
Mm-hmm.
All right, good. So close bracket. Simplify that bracket. You can simplify that without a calculator.
Okay. Yep. So.
Good. Is that it?
Yep.
Okay, so that's the exact answer.
Okay.
If your instructor requires an exact answer, that's the exact answer. Although, actually, if they don't require you to simplify, the previous one is exact too. In fact, the one we started, so I just don't know how much they want you to simplify here. You should double check with your instructor to see what you need here. Some instructors would care about this, some wouldn't. Let's double check that. Type negative 1 plus e to the negative 1 into your calculator and see what you get.
Negative 1 plus e to the bracket negative 1. Negative 1 plus e raised to the negative 1. I get a syntax error. Type in negative 1 plus e raised to bracket negative 1 bracket. Okay, yep, yeah, that's right.
So you got the same thing as before?
Yep.
So notice you can always check if your exact answer is correct by typing into the calculator and converting it into a decimal. So your instructor always gives exact answers in their answer key. Your instructor always gives exact answers, but that doesn't prove they're requiring that. So you should just ask them directly whether they're requiring that or not, so we know whether we should keep working on that. Okay, but that was a good process. You worked through that problem correctly. Again, you were careful with the signs. There were lots of negative signs running around, but you were very careful not to make any mistakes with that. That was good. I'll go back to my screen. So what we're seeing is if you need an exact answer, you kind of have to you can't do things in one step on the calculator anymore. I guess I have to reverse my earlier advice. Before I was pressuring you into always doing everything on one step on the calculator, but now I'm being flighty and changing my mind. If you need an exact answer, you kind of have to do it in pieces so you can see which parts come out to be even numbers and which parts don't. So it'll be helpful if your instructor just tells you what they're looking for there. Okay, so let me write this down. Try this problem.
plus 2 over 2, so 1/2 divided by 1/2. 2x to 1/2 plus 2 over 2 is 1/2 divided by 1/2 plus 6 over 6 is 5/6. So bracket 2 times 64 raised to bracket 1/2 plus 6 divided by 5 times 64 raised to bracket 5/6, and another bracket minus bracket 2 plus 6 divided by 5 bracket. Yeah, 51.2. And then check it. Bracket 1 plus the math cube root of x, close bracket again, divided by the square root of x, close bracket. Second calc, get there. Second calc, 7. 1 for lower limit, and 64 for upper. I think I need to change my format. Format, zoom fit.
Zoom fit changes the y-axis. It makes the y-axis fit, but your problem is your x-axis.
Okay. Go to my window. Change my x max to 100.
That's a good idea.
And go back to second calc. Second calc. Calculator's slow. Okay. 1 and 64.
Suspenseful.
Yeah, I get 51.2.
Okay, very good. Okay, so what does it mean if you get an error message when you try to do the second calc integration?
It means that I need to change my window.
Yeah, you need to change the x or the y.
Yeah, the x.
That's right. Why didn't we have this problem before? How is this problem different from all the earlier ones we did today? It's because there's a huge upper limit, right? The upper limit here is 64. Do you know what's the normal window on your calculator? Usually I think
10.
x just goes from -10 to +10. So the graphing will only work if you're just staying between -10 and +10. If you're going outside of that range, you have to go to the window menu and fix that yourself manually. Otherwise, this integration function won't work. Okay, well, we can see we got that right because it came out correctly there at the end. One moment. Let's see. And we got a nice exact answer. Well, you know, this was the problem, very similar to the problem that we did earlier today that gave us trouble, right? Earlier today, we did a similar problem to this that gave us a lot of trouble. But here, we got this problem correct. So that's some good progress there. That this is one of the harder types of problems that we've done. When we did a similar problem to this earlier, we got pretty flummoxed. But this time, I think you got through the whole thing in good form. Lots of chances there to make a mistake, but we didn't make any. Okay, I'll go back to my screen. Okay, so those are all the integrals from section 5.4. So we now know how to do all the different types of integrals and definite integrals and indefinite integrals from section 5.4. Unfortunately, there's one new group of anti-differentiation techniques in section 5.5. So there's still some more techniques we need that are going to build on these. These we have to be ultra confident about because these are just going to be steps in the last set of problems. But I think right now we're in good shape for the section 5.4 integrals. We're understanding those. 5.5 is, oh joy, even more antiderivative techniques, new antiderivative techniques. So you have to be ultra comfortable with all these that we did today. So I think we did very well on these today. I gave you 8 problems in a row from the website, and I think we were 100%. I think you got 100% of the website problems correct. That's excellent. However, I think we've seen sometimes in the past that it's possible to get a problem right on Saturday and then forget how to do it on Sunday. It's easy to start forgetting this material. So make sure that you practice those antiderivatives because, like I said, we're going to have to do even harder antiderivatives. So these have to be easy for us. These have to be easy for us because these are just going to be one small step of the next section of antiderivatives. So these have to be the easy problems so we can build on top. So that would be something that would be useful for you to practice. Practice. So I don't think I gave you any homework problems for the math yet. So let me write down something to do for the math section. Okay, let's make sure I copy this right. Okay, you have that in your notes?
Yep.
All right, great. All right, so let's take a look at this.
Okay.
Here. Take a look at what you have written down there. Okay, well, that looks like a good process for solving the problem. So here's the point. the output from trig functions often has the square root of 2 or the square root of 3 in it. The output from a trig function often has the square root of 2 or the square root of 3 in it. So go ahead and do that calculation again on your calculator.
Okay. So tangent of pi divided by 4 plus sine of pi divided by 4 minus tangent of 0 plus sine of 0.
Okay, good. Have we talked about how to store something in memory? Do you remember how to store that number in your memory?
Second mem.
Okay, good guess, but no, that's something totally different. You need to use the store key.
Okay.
Do you see the store key? I guess you're using it on your screen. But the store key is on the bottom left?
Right.
All right, and then you can put that in any variable you want. Most of the variables you'd have to use the alpha key for. If you put it in the X, you can use the X button. So I guess we might as well put that in X for the time being.
Okay, store X. Okay.
Okay. All right, now we were just saying that, yeah, you can follow along on my screen if you want to. So the answers for these problems, I took off the Skype, so you can go to my screen if you want. The answers for these problems often have the square, so the output from a trig function. The output from a trig function often has square root of 2 or square root of 3 in it.
Mm-hmm.
So let's check for that. Let's divide this by square root of 3. What happens when you divide that by square root of 3? What do you get?
By the square root of 3, I get 0.9855.
Nothing interesting, right?
Right.
All right, now let's try dividing by the square root of 2. But wait, how can we get back to the answer? How can you get back to the answer now?
Second enter.
Well, yeah, you could do that, but then you'd have to do the calculation all over again. What I meant was it's stored in X, right?
Okay.
So you can just hit X, and now let's divide the X by square root of 2. What do you get then?
1.207.
What? All right, 1 second. I thought that was going to work out so nicely. Let's see. Okay, plan B. Try again. All right, so figure out the tangent of 4.
Okay.
No, sorry, the tangent of pi over 4.
It's 1.
All right, very good. So I have to totally reverse my earlier advice to you. Before, I was trying to bully you into always doing everything on one step in your calculator, but that turns out to be totally wrong because you can't get exact answers that way. So now my new advice is to do everything in little steps. So we figured out the tangent of pi over 4, so I'm going to write that down as 1. Now we can do the sine of pi over 4.
Sine of pi over 4 is 0.707.
All right. Now you can store that as x. Try dividing it by the square root of 3. Does it come out to be an integer?
One second. Divided by... So I just press X.
Well, you can't use the old x. Or I guess you could, yeah. So did you store the new 0.707 in x?
Yep.
Okay, so then you can do x divided by root 3. Does that come out to be an integer?
No, 0.408.
So let's try x divided by root 2.
Okay. 0.5.
So now try to figure out what is x. You might have to work that out on paper.
Okay. So x divided by square root of 2 equals 0.5. So x equals 0.5 times the square root of 2. So 0.5 times square root of 2.
Good.
X.
Your instructor would probably expect this to be written as a fraction. How would you write that as a fraction?
X equals, wait, As a fraction, x equals square root of 2 times 0.5.
Right. How would you write that as a fraction? What is 0.5 as a fraction?
1/2.
So what would that whole thing be as a fraction?
Square root of 2 over 2.
All right, that's the answer.
Okay.
Let's check that now. You can type that whole thing into the calculator and see what you get.
Yep, 1.707.
Okay, so how can you get exact answers? I guess I have two pieces of advice. One piece is if you're getting an answer that's a weird decimal, it's a good idea to go back and just do the pieces separately. You have to do the pieces separately in order to simplify them. And then we need to remember the output from a trig function often contains what in it?
Square root of 2 or square root of 3.
That's right. And we just went over how you can check for that by dividing by root 2 or dividing by root 3. Now, the output from an inverse trig function often contains what?
Output from an inverse trig function often contains.
This is something we've talked about in the past.
Square root.
So what we said previously is it often contains a multiple of pi.
Okay.
Output from inverse trig functions often contain pi. So these are two things you can check for. You can divide, but you can see it's not good enough to divide the overall answer. The overall answer is oftentimes too complicated to work out on your calculator. So you kind of have to break these up into smaller steps. You have to break these down into smaller steps so that you can see the first time that you get a weird answer and you can simplify it, if that makes any sense. So it might help to memorize these ideas. You know, if we had an hour, I could just teach you how to do this correctly. If we had an extra hour, I could just teach you. It's not rocket science. I could teach you how to predict these and how to figure these out. Maybe 2 hours, but maybe that's not the best use of our time right now. So I'm trying to give you kind of a shortcut.
Okay.
All right.
So basically, when I get to the end of my answer, I can check to see if tangent of whatever is a whole number. So I keep that and I move on to the next one. And if that's a decimal, then I try and rework it to where I can rewrite it as, okay.
Yeah, that's right. So the point is I'm reversing my previous advice. My previous advice was to try to do the whole calculation in one step on your calculator. That turns out not to have been good advice because that makes it hard to get exact answers. So my new advice is the opposite of my old advice. My new advice is do the calculation in small steps so that you can see the first instant where you get a weird decimal. Now remember, if you get a decimal like this, a decimal like 0.25 or 0.21, that's no problem. The only thing your instructor won't let you get away with is a decimal that goes on forever. All right, if you get a short decimal like 0.5 or 0.25, you can just put that in the answer.
Okay.
The only thing your instructor doesn't like is when you have a long non-repeating decimal. That's when because then you're not really giving the exact answer. Okay, so in any case, let's go back to your screen and finish looking at those homework problems. All right, so that was a bad answer from your instructor. I was hoping it was going to say he didn't care. He didn't care about the exact answers, but it turns out that apparently he does. All right. Let's see. All right. So that first one you got correct. That's good. Except that we didn't write down the exact answers. It would be good to go back and redo it so you can review how to get the exact answers there. Let me look at the next one. Okay. This wasn't the problem that I meant to give you. Either I miswrote the problem or maybe you miscopied it. The problem I meant to give you was t times 4t squared minus t. So we'll make that a new homework problem.
Okay.
Oops. So, oh, did you copy it from the notes I sent you?
Yep.
Well, that's not fair. You just showed who just screwed up. I didn't know you had that. All right. Well, I got egg on my face. All right. So it looks like I messed up and I gave you the wrong problem, and you succeeded superbly in answering the question that I gave you. Very good. All right, that's what I get for sending you my tutoring notes. All right, very good. So you're absolutely right. Given the problem that I sent you, that was the exact right answer. Okay, so good job. That's correct. That looks like a good, careful approach to that. You may as well treat this new problem as the new homework problem, so since that's the one from the sample test. 0 to 1, t, 4t. All right, yeah, but that was my mistake the first time around. Okay, good. So it looks like you got those two correct. And then I redid
the problem where we had... I did the wrong version of this problem yesterday, but redid it.
Let's see. T4t. Right, that's a polite way of saying I gave you the wrong version of the problem. Good. All right, and now we have the correct version, and it looks like I did that correctly. All right, so we put a lot of time into that, and you worked that out. Here, you had to use the distributive law before you could do your integration, and it looks like you worked that out. Okay, good. All right, excellent. Okay. All right. So those first two problems where it says find the general indefinite integral, and I think you misinterpreted what your instructor meant by that. So your instructor meant you to actually find the indefinite integral. They didn't mean for you to use the sigma notation. So this, I guess what I'm saying is they're going for the short way. Or really, there is no long way or short way here because those are not definite integrals.
So the antiderivative.
Yeah. What's another word for indefinite integral?
The antiderivative.
That's right. Well, so we'll make those a new homework problem.
Okay.
So you can try them again. So that's one reason why it's good to do problems, so we make sure we don't have any misunderstandings about the way they phrased it. Notice how you wrote down there below, long way to evaluate definite integrals. Mm-hmm. But notice that those two problems up above, those are not definite integrals, are they?
No.
No, they're indefinite integrals. Okay. All right. In any case, right. So there isn't any really long way to evaluate them. Without limits of integration, there's no such thing as a Riemann sum. Without limits of integration, there's no such thing as a Riemann sum. Okay. All right. So you can try those again. Now we see more clearly what the instructor was going for. 1 plus cube root of x. Okay. And what's the symbol that you use to show the end of a definite integral, the dx? So we should add a dx to your second line. That's like putting in a right parenthesis, kind of. Okay, all right, good. So we haven't done any of those for a while. 1 over root 3 is a little bit tricky because there's 2 algebraic manipulations you need before you can take the antiderivative, but you did that correctly. Remember that I actually gave you this problem yesterday too. But when we had this problem yesterday, what you wrote down was something like the limit as n goes to infinity. I think we had misinterpreted the question. So remember, that's what I meant when I said it's important to make sure you're answering the right question. So that whole limit as n goes to infinity, first of all, that only applies to definite integrals, not to indefinite integrals. And you only want to use that when they give you a clear indication in the wording that that's what they're going for. Okay, and then we have the second problem. Let's see. Okay, let's go to my screen.
Okay.
Is there any way to rewrite this?
Yep, we can rewrite this as a over d plus b over d plus c over d.
How can you check that that was legal?
We can add them together
Uh,
and see if we get a plus b plus c over d.
And do you?
Yep.
How do you add fractions?
You just put them together, I think.
Can you be more specific?
You add the numerator,
So
a plus b plus c.
could we just add the numerators here?
No,
Why not?
I'm not. Because you need a common denominator.
Yeah. So these are not ready to be added. You'd need extra algebra to add them. Before you can add them, you need a common denominator. Good. Is there any way that you can rewrite this expression?
You could rewrite it as a no, you can't.
Can you do this?
No,
How can you see that this doesn't seem to work?
because you don't have a common denominator.
So you can't add them and get back this.
Right.
That's right. Okay, but I think this is what you tried to do on that last homework problem.
Yeah. Okay.
So that's a tricky thing in math. One thing that's important in math is to know what's legal, but it's also even more important to know what's not legal, so that you can't treat those the same way there. Okay, so that one gave us some trouble. Let's see. Let me write that problem down again. So that was... Okay, so here was the problem, and I think you ended up doing something like this.
Mm-hmm.
So is that a legal step?
It's not.
No, because we can't split up the denominator there. We can't split the denominator. We can only split the numerator like this. So we're going to need some totally different approach.
Okay.
Any other ideas?
Let's see. Can we just bring the x squared to the top?
How would you write that then?
X to the negative 2 over 1.
Let's see. Well, the way to tell that is by taking baby steps. So suppose you had... Suppose you had this. Do you agree that that can be written like this?
Mm-hmm.
How can you tell that this is legal?
Because when you multiply those two fractions together, you get 1 over ax squared.
That's right. And is this legal?
No.
And why not?
It is legal. Yep.
Yeah. All I've done here is I've just said that 1 over x squared is x to the negative 2.
Mm-hmm.
And is this legal?
Yep.
Yeah, how can you tell?
Because if you bring x to the bottom, it matches 1 over a x squared.
Okay, well, the problem is that we're trying to test whether that's true or not. The real way to check is to do this and multiply. If you multiply these two fractions, what do you get?
X to the negative 2 over a.
Yeah, so now we can see that this is a case. So my point is it legal to bring the x squared to the top here? Well, yes, but the only way to be sure is to take these tiny little baby steps. That's the way to improve our confidence in algebra, by taking little steps and making sure that each of them is legal. Now let's say we have this. Is this step legal?
No.
No. You can see that because if you multiplied these, you wouldn't get this back. And is this step legal?
Nope.
No, we were just talking about that earlier. But this must be what you were thinking of when you moved the x squared to the top. You must have been thinking you were going to do something like this. You were saying that you could move the x squared up to the top of the fraction here, but you can't do that because there's no way to get past this step. This step is not legal in this case. All right, so in any case, it turns out that no, we're not allowed to bring the x squared to the top of the fraction. I know it's tricky to improve algebra skills when you're in the middle of a calculus class, but one thing I would recommend is try to take smaller steps. Instead of saying, I think I can move the x squared to the top, ask what would be the tiny little baby steps that you would use to try to move it to the top. And then if you can make up a sequence that works, then that's how you know that that's legal. Okay, well, in any case, so it looks like there actually is no good algebraic. So one of the things you're trying to do here is a good idea. You're trying to algebraically simplify this fraction. You're trying to algebraically simplify this fraction. That's oftentimes a really good idea. It's a good idea to try to algebraically simplify fractions before you take the antiderivative. But there doesn't seem to be any way to do that. This is really just about as simple as we can get. There's no way to simplify this, so we need some other approach. I'm sorry, had you said something?
Yeah, I think it's inverse tangent.
Yeah, that's right. So that's what we should have been thinking of here. We don't need to simplify this because we actually already know how to take its antiderivative. Okay, all right, so we went over why the algebraic approaches didn't work. Now that you've thought of that, maybe we can get through the problem again. So why don't you try the rest of this on your screen?
So the derivative of inverse tangent of x is 1 over 1 plus x squared. Okay, I think that's good.
Okay, all right, well, that would be an important one to mark. So that would certainly be an important thing to go back and review. So we spent some time on that before, but that's something that's easy to forget. I can see how we could get confused here because in many cases, you really do want to try to simplify things algebraically in order to take the antiderivative. So this is kind of breaking that pattern. So it's just something that has to be learned separately. So I think now we had that correct. All right, I'll go back to my screen. Okay, well, let's try this problem on your screen.
plus 1, negative 1. And this is sine x. So I rewrote this, x to the negative 2, and 2 times 1 over square root of 1 minus x squared, respect to x, antiderivative plus 1, divided by negative 1, negative x to the negative 1, constant multiple rule, and then we have to see that this is the derivative of the inverse sine of x plus. Okay.
Okay, that's correct. That's correct. So notice we didn't try to simplify the square root algebraically. We just used our inverse trig function. I'll go back to my screen. You did that correctly. Okay, let's try this problem. All right, well, I was trying to confuse you by putting that 1/2 fraction in, but you handled that correctly. It's just a constant. So you did that correctly. Okay, so that's just more practice with those inverse trig functions. Okay, so that's the purpose of those homework problems, to give us a chance to re-review some stuff we went over earlier, so it looks like that came in handy. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the annotation. Thank you.